Okay, we're back at it, and we're talking about more refractive index. How long can this guy talk about refractive index? What on earth have I signed myself up to do? Well, good news, you learn it once, and then that makes the other class way easier. So if you're taking 115 first, when you go to 114, you'll know exactly what we're doing. And then if you took 114 first and you're in this class, you know exactly what's going on. So that is one of the reasons that we talk about it twice, just to get you to kind of face that little demon all over again, because that's how we tackle them and that's how we conquer them, right? All right, so we just talked about the various uses of refractive index. So we're focused on general chapter 831, and I told you that we're going to go in and we're going to take a look at 831 as far as the USP has listed it. So here is the USP entry for 831 general chapter refractive index. So we're going to go through like we've done before and read some important information. All right, so refractive index is the basic physical property of pharmaceutical materials. This general chapter only applies to the measurement of liquid pharmaceuticals, solutions, solvents, and liquid raw materials. Oh, God, that's going to be a trick question. Refractometers can measure solids and gases. We can get refractive indexes of those states of matter. However, the USPNF in this very first sentence says probably the only time that we're going to use refractive index is measuring liquid materials. That is it, because it tells me measurement of liquid pharma, solutions, solvents, and liquid raw material. That is it. Nothing more. So there's a chance that if this stuff is a liquid, there's a refractive index that's tied to it. There's a chance if it's a solid, I'm never probably going to be required to take a solid and get a refractive index according to USPNF standards. It also says with standalone instruments and not to detectors of chromographic systems. Well, what on earth is that? Well, that's for a different class. That's for our chromatography class, because refractometers can be paired with other instrumentation like chromatography systems in order to provide data. So these standalone instruments are standalone refractometers that are sitting on a bench top ready to be used. That is what we are after, nothing more. Very simple, easy to use, takes just a few minutes to clean, load a sample, write down a number or print off a number, and then call it a day. All right, so it says refractive index measurements of liquid pharma, solution solvents, and liquid raw materials are useful for the following. We are, number one, going to identify a pure substance. I hope so, because I want it pure before we use it to make something in a manufacturing lab. Number two, establish the purity of the substances. So again, if I know a little bit about the refractive index values and what they should be, then I can use a little bit of math, a little bit of algebra, solve some X's, and then figure out actually how much is present. So is it 95% pure? Is it 90% pure? Is it 99.9% pure? That's what number two is after. Three, determining the concentrations of some solutions, such as alcohol or sugar. So, for example, percentage of sugar in syrup. Yeah, so I can take maple syrup and I can analyze that on a refractometer to see how much sugar is present. I can take pancake syrup and do the same thing. I can take various sodas off of a manufacturing line. So if I'm working for Coca-Cola, pull those samples off, let's run them, let's see how much sugar is actually there. Alcohols are the same way. I can take beer samples, run them, how much alcohol is present. Wine samples, run them, how much alcohol is present. Tequila samples, my favorite. So take that, put it on a refractometer, see what goes on. It used to be rum, but I think I just drank too much rum, and tequila is now my new favorite. But I could still do rum on a very hot summery day. Next, determining the uniformity of final compounded preparations. So if there was a manufacturing piece that went on and they have made something, they want to check the purity of what they have made. So I'm going to take their final product that they have ended up with, and then we can take that final product into a lab, put it on a refractometer, get a value, and then report that value back to the formulation department or to the manufacturing department and be like, yep, you made it the right way. Looks good. This is a checkbox. So keep doing what you're doing and everybody's going to be happy and everybody's going to get bonuses. All right, next. The refractive index of a substance or medium is defined as blah, 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 blah. All right, and that's exactly kind of what I want you to do with that paragraph. I'm not really interested in this. There's a few numbers, though, that I want you to pay attention to. The first one is 589 nanometer. So in the USPNF listing, 589 is specifically stated. So it says that, for example, the refractive index of pure water at a measurement temperature and wavelength of 20 degrees and 589 nanometers is 1.3330. So what they are after here is this idea that, yeah, temperature's dependent, but your light bulb is important as well. The light energy that you are using in this measurement, we are stating, needs to be 589. And that's the sodium D lamp that we talked about. So it does specifically say sodium D here. Now, there's different options. There's different ways that we can monitor these things, but 589 is up front and center, especially up there at the very top. When they list refractive index for you, they will list them a couple of different ways. N is always this abbreviation that they use for refractive index. It's always going to be N. And my cursor just won't highlight that. But it is a lowercase n for refractive index. So when I look at this reference book, or when I look at this reference table, and I see all of these values and numbers that are listed, sometimes they will not write the word refractive index. Instead, they will give me a lowercase n, and that is what that represents. The number below, which is the subscript, in your first option that you see here says 589. That is in regards to the nanometers of the light energy that is coming from the bulb, 589. Very often, though, they do not write 589 because it makes it messy. And instead, what they'll do is that they'll write a capital D down there below. And that capital D represents sodium D. That is what that stands for. So they are telling you this measurement was obtained by using a sodium D bulb in the machine that you should be running. So 589 or D means the same thing. The superscript up on top, that superscript is going to be the temperatures. So that temperature is going to be in Celsius. So 20 degrees Celsius using a sodium D bulb. And if you meet those criteria, you should get a value of 1.3330. All right. So that is how refractive index is listed. That's how all reference texts are listing it. And that's how the USPNF regards it as well. All right, so now that we kind of get this gist of what this refractometer is, I'd see a section now that says qualification of the refractometers. And there's actually three: IQ, which is installation, and then OQ, which is operational, and then PQ, which is performance. And it says, listen, if you want to know more information about installation or the operation or the performance of your machine, all of these Q's that go on in a lab that somebody's going to have to do, then you need to refer to the analytical instrument qualification, and that's General Chapter 1058. So that's going to be talked about at a different moment in time, probably within a different course, but the IQs, the OQs, and the PQs are very important for a laboratory, and they have to go through these motions in order to kind of do their job the proper way, and especially when we use instrumentation and equipment in the laboratory setting. So the installation qualifications, it just says, well, it provides evidence that the hardware and the software, if appropriate, are installed the proper way. That's really all that is. Installation, that makes sense. The operational qualification says, well, the operational version of a refractometer should verify the temperature of the machine. So somebody's got to make sure that when I type in 25, 25 is actually getting heated up to or cooled down to, right? I just don't want to type in 25 and assume that the machine's going to 25. Someone has to double check it, and this is an operational qualification. It says the apparatus should provide a refractive index reading of 4 digits at least, based on USPNF standards, and it should provide a means of operation at the temperature within +1. So they're even tighter on the temperature read. So if I type in 25, it better not be 25.5 that it heats up to, because that's going to change my refractive index value, and that's because that temperature is not appropriate. So I want to make sure that when I do type in a temperature readout, it is really at that temperature, or my instrument is not performing the proper way. The certified reference material must have an equal or better expanded uncertainty, blah, 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 blah. Then they talk about accuracy, how close should you be? And then they talk about repeatability. How close are those measurements if you repeat them one after another, after another, after another. Finally, the performance qualification, it says, includes 2 stages, periodic instrument calibration and performance evaluation. The instrument calibration should be performed periodically, and the second stage, PQ evaluation, should be conducted at a regular interval. So again, discussions for another day, but I want to make sure that when I record a value from a reference standard, that my machine is providing me the expected number. And it's not due to a phony, contaminated sample, right? If my numbers are off. It could be due to the instrument that is off. So periodically, we've got to go through and we've got to make sure this instrument is performing the proper way. Hence, performance qualification, right? Procedures, sample preparation. It says samples should be kept in a well-closed container to protect them from any changes. So very often, if we're in an organic lab or if we've got some type of solvent that we're using, these can evaporate off very easily. If they evaporate off easily, then I'm going to get a composition change and my refractive index is not going to be the same value. So I just have to be careful, and what this means is that I got to place lids on things, right? I got to keep them in containers, I got to put lids on them, and if they are volatile, I probably want to chill them until I'm ready to actually run them. And then I'll bring them to the proper temperature that they should be analyzed at. Next, if the sample is to be evaluated is not homogeneous, or is hazy, or has suspended particles, or an emulsified phase, think of like a thickening agent here, factors that all influence the measurement, you've got to clarify it up. So we do that by either filtering it through a membrane filter or a regular piece of filter paper, or we centrifuge it so that way any of those solids or that chunky, heavier material can fall to the bottom of the centrifuge, and all of the kind of clear, nice, neat liquid is going to be up on top, and I can just suck off from the top layer, place it on a refractometer, and get my reading. Measurement procedure, in the USPNF it says, okay, follow your directions. I mean, that's really all that it does. So based on the instrument that I have, the operation is going to be different than what someone else will have. And the USPNF is not going to bother here. They're just going to say, go to your instrumentation manual or your instruction book. Follow those instructions and then report the values as you follow those instructions. It says, unless otherwise indicated in the monograph, the refractive index is measured at 25 degrees. So I did not lie to you. Even though they mentioned 20 up above, it's not a big deal. They were just kind of describing something. But all of these measurements need to be 25 unless otherwise noted. And the reference wavelength is the sodium D bulb. That is what they prefer at 589. So don't think that you're going to get fancy, because 589 is really the only thing that's approved in order to report these refractive index numbers. And hence why most refractometers have to include a sodium D lamp at 589 because they know this is what's required with the USPNF, as well as a large portion of the laboratory community. So all of these instruments are going to have to be made in a very similar way. All right, so that's a little bit about General Chapter 831, Refractive Index. Now, I also told you that I wanted to show you kind of a video of someone using a refractometer. And what you're getting ready to see is one version of a refractometer. And I'm going to kind of overlay my voice onto what they're doing. And then we're going to start taking a look at images of other versions of refractometers that might be out there. All right, so this video is just going to be found on the latest and greatest YouTube, but this is someone using an actual Abbey refractometer. Ours model is a little bit different than what you're going to see here, but it is something that basically has the same operation. The knobs may be found in a different place, or the way the sample's loaded up might be a little slightly different, but overall the concept is all the same.
Correction.
All right, so what you're seeing on the screen right now is the side view of a refractometer, at least their version of a refractometer. So you're seeing a knob that's here that they're calling the main adjustment knob, and then up here you're seeing another one that's called a dispersion correction. I like to somewhat call these the main adjustment and the fine focus, because there's going to be a moment where things will look a little hazy, and what you're doing is that you're just fine-tuning that meter up a little bit so you can quickly see a division. What am I talking about? If you've never used a refractometer, that's to come, because this video will show you the view of what you'll see when you look into the machine. Up here on the top, these are going to be the eyepieces that you're going to look through. Our models only have one. This model has two. Our model has one because there's a nice little flip switch that takes that one viewfinder and it will flip it back and forth between the light that's coming through and the meter that you need to read.
A number of other controls that we will now look at in turn. On this model, there are two eyepieces, a prism viewer and a scale viewer.
All right, so prism viewer would be the light energy that's coming through, so you can see light and dark halves. And then the scale viewer is going to be a meter that is associated with that light energy. Again, our version is one eyepiece, and there is a toggle switch that will allow you to go from one viewpoint to the next.
If we look through the scale viewer, we can see the measurement scale.
This is what you'll see when we actually write down the reading that we are getting from the manual operation. A lot of people, I think, have trouble just orienting themselves on how to read this meter. This tall line here is 1.330. And I want you to take a look at the division marks here. So 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10. So this is 1.330, and that's 331, 332, 333, 334, 335, 336, 337, 338, 339, 340. That is how that division bar is kind of oriented. Down here at the bottom, this is just a different scale that we don't really pay attention to at all. This is for a bricks, and we never really measure bricks in our laboratory, but bricks is in reference to sugar concentrations most of the time.
The upper of these is a refractive index scale. The lower of these is a brick scale. We will use a refractive index scale.
And we do too.
If we look through the prism window, we can see a prism viewer. This allows us to line up the scale so that we can make our reading. You'll notice that there's a light area, crosshairs, and the dark area.
So when you load a sample up, this is what you're going to see in the viewfinder of our refractometers that are manual. There's a light half and a dark half. It will never be already aligned like this. There will be probably more light or more dark depending on what you've placed onto the machine. And it's our job to get this division between the light and the dark smack dab in the middle. That is where we want this readout to be. All right. So that's the crosshairs. And right now, this is pretty good. I mean, this is almost smack dab in the middle. So the top half is light and the dark half is dark, of course. So that's what we're after.
The refractometer is also equipped with a thermometer, and the thermometer measures the temperature of the sample when we make the measurement.
So our thermometer is not digital like the one that you saw in the picture. Our thermometer is more of a actual thermometer that is placed on the side of the refractometer. So that way you can record those temperatures when you make those measurements, but ours do not have a digital display at all. So ours is a little bit older than what you saw in the picture.
Refractive index changes with temperature. So in this picture you can see that the air coming out of the back of the jet is much hotter and so appears rippled against the cool air which is elsewhere. This is also responsible for the phenomenon of mirages. Here we can see the prism in the closed position and the light which is built into this particular model of refractometer.
So the light bulb, which is sodium D, is right here. That's that orange light. And that orange light is getting directed at this prism area, and that is going to be located right here. That's the entry window. So that means that the sample is going to be placed underneath this stainless steel sample cell. So this is going to open up, and you'll put a sample there, and you'll close it back so it doesn't evaporate or disappear on you. And then the light energy will go in and hit that liquid substance, and we can get a reading.
If we open the prism, we can see where the sample has to be placed.
And there's the prism right here. And you can see some liquid on top of that prism.
Okay, so let's use a refractometer and measure a refractive index.
All right, so there it is,
First thing we
open.
do is open it up and clean any excess sample that's there. Next we want to clean the prism really well.
And we normally clean it with acetone or methanol, depending on what we actually have on there before. Acetone makes a great solvent, methanol makes great solvents, but acetone is nearby almost every single time with our refractometers. So that's normally what we use when we clean and prep these instruments.
Well, for our sample, so we spray on a little acetone, both faces of the prism, and then we wipe it clean.
And notice he said both sides of the prism. There is a top surface contact and a bottom contact that touches your sample. So a lot of people will clean the bottom, but they don't clean the top one. And if not, you're doing cross-contamination. So you want to make sure that you clean the top portion of the sample compartment as well as the bottom one.
Give it a second or two to dry, and it's ready for use. So once we're ready to go, we'll take our sample and we'll put it onto the prism. The earlier photo you could see it in place. We'll see that again.
So sample
we add
goes
a few
on.
drops, just enough to cover it completely so that when the prism is closed, there is a full layer between the two.
Doesn't take much. Few
You can
drops.
see sufficient sample to cover the window.
Just make sure that window's covered.
So we'll close it, lock it into place, and it's time to make our measurement.
And-
Wipe off any excess,
And
put the line
now
into position,
sodium
let's
D
go.
goes up. And the eyepiece.
So I look through both viewers, make some adjustments, adjust both settings, and then I can make my measurement. Simple as that. Well, let's slow it down a second, see what did I actually do. So first things first, what do I see when I look through the viewers? Well, the first viewer I'm going to look through is the prism viewer. So I'm making two.
All right, so like I said, most of the time when you put a sample onto the instrument, you are not going to hit this division line smack dab in the middle. So there's the crosshairs, and it's going to be our job to lower this black half down to the crosshairs. So that's going to be the main adjustment knob that we're going to have to deal with first. That raises and lowers this dark half to make sure that we have it at an appropriate level. So this person's going to have to take that main adjustment knob and lower this black area down until it gets to the crosshairs. That way the top half is light and the bottom half is dark.
Two adjustments in this section. First, you can see that I'm bringing the line into sharp focus, and we'll slow it down and have another look in a sec. The second adjustment is that I'm moving the position of the transition between light and dark to line it up with the crosshairs. So if we go back and we have a look at this, click back to it now, we can see that the colours slowed down 8 times here are changing very slowly. There's a green tint, and then that goes to a red tint, and then eventually I get it just right so it's back at being a sharp line. and that's controlled using the dispersion control wheel, and you have to adjust that for each different liquid that you measure on the reading.
So he's talking about this hazy line that's up here at the top between the light half and the dark half. So very often, depending on what the substance is and your own eyeballs, you might see this area here a little hazy or a little fuzzy. And it should be a very crisp division line between them here. So the fine adjustment dial will allow you to dial that back and forth and kind of sharpen that division line between those two halves. And that's really what he's talking about here.
Refractometer. When you have that set up, then you have a nice...
So notice he's turned that fine adjustment knob back and forth just a little bit. And the green now has disappeared. And it's more of a fine division line now, right? It is a strictly light half and dark half. And there is the fence that both of these reside over.
Nice clean line, and then you can go back to setting it up so that it's exactly lined up with the middle of the crosshair that you can see in the middle of that circle. So if we look back at it, we can see a clean, monochromatic, sharp line that is lined up perfectly with the crosshair. So if we switch our attention to the scale viewer, we can make our reading. It might be an idea to push pause now.
So here's the meter reading. And you would have to record manually what you're seeing from the scale. And again, for this refractometer, these are ones. So 330 and 331 and 332 and 333. And then there is a line that goes straight up and down right here, right? Straight up and straight down. So I need to go to the reading that is right there. So notice it is past 333. But it's before 334. So how do we fix it?
Take some time and stop and see what the reading actually is. I'll show you the answer in a second and you can compare it to see what you got. So to me, that came out as 1.3336, 4 decimal places. So here's the chance to try another one. We load another sample, and what do? We adjust both our settings. So we adjust the dispersion control and we adjust the main control, we line it up, a solid black line, exactly with the crosshair, and then we can make our reading. Once we finish adjusting that, there it is, spot on. We can turn our attention to the scale viewer. Again, pause the video, see what number you get, and then I'll show you the answer and you can compare. Remember to read from the upper scale, that's the one that we're interested in, and I get 1.3591. What material might this be? Well, let's have a look in the Aldrich catalogue and we see that acetone has a refractive index of 1.359. It's probably acetone. Here's another one. Try reading this one. Again, pause if you need to. The answer's coming up in 2 seconds. 1.3609. And finally, one or two other things to look at. Not all refractometers are exactly the same. Some of them, the scales look slightly different. In this one, the upper scale has taken out the 1 point before the 1.35 or 1.36. It's still measuring refractive index. In this one, you can see both the prism and the scale through the same window. So the upper is brick scale, the lower is refractive index. The same thing, just a slightly different layout.
All right, so that's how we read a more manual refractometer. We have them, we get you to use them, not in 115, but in 114, and we keep the technology piece really up front and center in the 115 class. So with that said, that's where I'll stop this video. In the next one, we'll talk about the equipment. We've already seen one now, so what are some of the other versions that this refractometer will show up in? And we'll talk about the slight differences between them. And I'll see you then. So come back and see me. We're almost over, believe it or not.